All right, so the law of multiple proportions is a more difficult one to understand. The definite proportions law is pretty straightforward. This one is not as straightforward. So the best way to explain it is with an example, not saying the words. John Dalton is the one who formulated this law in 1803. And he discovered this. He took 100 grams of carbon and reacted it with 133 grams of oxygen to produce carbon monoxide. Then he took 100 grams of carbon and reacted it with 266 grams of oxygen. And that produced carbon dioxide. And so what he did in this example is he took a fixed mass of one of the elements. He kept one of the amounts constant. And then he changed the mass of the other reactant.
So if you double one reactant, it can change the compound?
Exactly. And so he determined that you can look at the same elements, but in different proportions. And based on different proportions, you might get a different product. So that's the first part of this law. There's two parts to the law, but that's the first part of it. And then what he did is he took a ratio of the two masses. For this reaction right here, he took the mass of oxygen divided by the mass of carbon. So 133 divided by 100. That equals 1.33. The same thing down here. He took the mass of oxygen over the mass of carbon. In this case, it's 266 divided by 100. That equals 2.66. And then what he did is he took these two ratios right here and divided them by each other. So he took 266, 2.66, and divided by 1.33. That can reduce to 2 over 1.
Would it just be 2?
It can also be 2, yeah, same thing. But when looking at ratios, they usually put a 1 in there too. But you can definitely also just say 2. So it's double what we have. So his law states this, that when you have a fixed mass of one element, you change the mass of the other element, you'll get different reactants, or different compounds that form in the products. Then you take the ratio of the two masses of the elements. Take the two ratios, divide them by each other, you get whole numbers. So you get a whole number ratio when you divide the two ratios from each other. So that's what the law states, and that's how we did that.
So what does the whole number ratio represent?
What it represents is that atoms are not divisible. You can't have half of an atom, a quarter of an atom. And so this was evidence for atoms' existence. Because no matter what he tried, he never got ratios that were fractions. And he said, well, that must mean that we're dealing with atoms that cannot be divisible. You can't break it down in half. It's just one atom or two atoms. We don't have half of an atom.
Why would the 2.66 be over the 1.33? Why wouldn't it be the 1.33 and the 2.6? Cause like,
Oh, you could do that either way. I mean, like, you could certainly do that. We just decided to have the ratio of this over that. But you could also have the ratio of 1.33 over 2.66. I mean, you could
what if
also,
I give a different result?
you'd be 1/2, but it'd still be a whole number ratio. It's still 1 to 2.
Okay.
So it's still, we're still dealing with whole numbers either way. Okay, any other questions about that before we go on? Does that make sense? Because that's the harder law to understand, but do you think you understand that?
So if you keep the first element the same and you change the second element, you will get a different compound.
And so that's the first part, but also you then take the ratios, divide the ratios, and get a whole number. That's a part of the law. That's important to remember.
This was turned in that homework yesterday, right?
Yes.
It wasn't due until like.
Yes, that's exactly. All right, well, for homework today, it's chapter review. Questions, we're gonna look at chapter review today, tomorrow, and on Thursday, with the testing Friday. So let me give you those questions to work on for the rest of class today.
You know it is.
Yes. So for today, work on 31 to 55 on page 94.